Okay, so far we've only really thought about electrophilic addition to symmetrical alkenes, like ethene there. So we draw what happens there. So we get HBr. We've got a partial positive on the hydrogen. The pi bond breaks, goes onto that hydrogen. Now, so what happens is we could say, right, the hydrogen, we could consider it, we could say, right, it could stick to that carbon. Yep, in which case we would have that one being the carbocation, or equally, it could have gone to the other one. It could have gone to the one I've drawn on the right, in which case the other carbon would be the carbocation. Then what would happen then is the bromide ion would react with either of those. And it wouldn't really matter, would it? Because they both make the same thing. They'd both make one bromoethane, yeah. Be the same product for each one, so it wouldn't really matter. Now, let's now have a look at the situation where we are going to have an alkene which isn't symmetrical. So the simplest one we could choose would be propene. Okay, so if I draw propene here, now we can see there that what can happen is the hydrogen from the hydrogen bromide, it could sorry, I've got too many hydrogens I want to talk about. The hydrogen from the hydrogen, you could either stick to that carbon, in which case you get the bromine on the middle one, the final product, or conversely, you could get the hydrogen sticking to the middle one, and you could get, so you'd end up with the bromine there, you'd get one bromopropane. So let's have a look at those, and we'll see that one actually is favored over the other. Right, so let's draw our propene here. I'll draw it like this to save it's okay. Right, so here's our HBr. And the electrons come off the pi bond and go into there. Simultaneously, this bond between the hydrogen and the bromine's got to break. So let's draw two arrows. Let's have it on this one. We'll have it sticking onto the first carbon. We'll have the carbocation there. And then that's going to react with the bromide ion. Lone pair from the bromide goes onto there. And you will form CH2Br1. You form one bromopropane. Let's have a look at this one here. And we're going to have the carbon sticking on the hydrogen sticking onto the other carbon. So we're going to get H3. That's going to be a carbocation now, because the other hydrogen is going to stick onto this carbon here. Right. And we are going to form there two bromopropane as the product. Okay, so put a circle around these carbocations, positive thing there. Now, if you do this experiment, you find out that you get a lot more of this one here, and that is called the major product. You get more of that than you get of that one, which is called the minor product. And if you want to remember a way of the major product is, well, the carbon that has already got the most hydrogens gets the hydrogen. So in other words, like this one already had 2 hydrogens, whereas that one only had 1 hydrogen, and the other hydrogen sticks onto this one here because it's got more. Right, but that's just a quick way of remembering it. It doesn't really explain anything, and we need to be able to explain it. Right, the reason for this is the stability of the carbocation intermediate. Right, this one is called a secondary carbocation. So I usually use, I'll move that down. This one is called a secondary carbocation. Well, secondary, that sounds for secondary. And this one is called a primary carbocation. And the way you characterize these is you say, right, this is a primary because if you look at the positive charge carbon, it's only attached to one other carbon. That's why it's a primary carbocation. Whereas if you look at this one as a secondary carbocation, because if you look at the positively charged carbon here, it is attached to 2 other carbon atoms. That's why it's called a secondary carbocation. Now, secondary carbocations are more stable than primary carbocations. This is more, carbocations are all unstable, but that one is more stable and this one is less stable. Okay, so this one forms more readily because it's more stable, and so you end up getting more of this product of the that's why you get that as the major product. Let's just talk a little bit about what causes the stability of carbocations. Okay, let's just have a little talk, think about that. Okay, so if I draw I'll draw a primary carbocation here. That would be a primary carbocation. Let's draw a secondary carbocation. So we'll do 3 carbons there and the positive charge in the middle one, attached to 2 other carbons. So that would have just 1 hydrogen there. This is a carbocation. It's only forming 3 bonds, the carbon. That would be a secondary carbocation. And you can, of course, have a tertiary carbocation. I'll draw that here. Some room down here, yeah. Okay, tertiary carbocation. Well, sorry. So we'd have to have a carbon here. And that would have to be attached to 3 other carbons. So I'm going to put a positive charge on that. So if I say that's CH3, that's CH3, and that's CH3, that would be the simplest tertiary carbocation. Now, why is the primary the least stable? Right. The reason for that is alkyl groups have a slight electron donating tendency. Okay, so if you look here, for this one, you've got 1 alkyl group. Quite often I draw a little arrow like that. That means this alkyl group here is pushing a little bit of charge away from itself into the carbocation. That makes it slightly less positive there. Okay, so I'll put 1 alkyl group donates charge. Well, here with the secondary, you can see there are 2 alkyl groups. There's that methyl group there, and that one methyl. And again, a methyl group is as good as an ethyl, is as good as a propyl, is as good as a butyl. It doesn't matter how many carbons are in it. It's just the fact it's an alkyl group that makes it donate charge. So that's got 2 alkyl groups. donating a bit of charge. So that is going to be, that positive charge is going to be slightly less intense than that one, because you've got two lots of alkyl groups pushing in. That makes it more stable. And finally, this one has got 3 alkyl groups. Donating charge, so that's the most stable. So you can see here, as you go down here, right, the carbocations become more stable. Okay, so there's quite a lot to take in with that, so I think we'll leave it there.